Okay. Questions?
Do you have to know the mechanism to
A couple. A couple of them you would need to know the mechanism of. What do I normally ask? Sometimes, let me go through and sometimes, well, the mechanisms that I usually, bless you, or that I have asked in the past are, the first one is when you take the phenol and you react that with base and CO2 to add, in essence, a C double bond O. You add a carboxylic acid at the ortho position to the OH group. So that mechanism is actually something that we could that we can do. So that's one that I've asked, and the mechanism for that was simply to deprotonate the OH so that you form the alkoxide ion. And then we already know that from the reactions of Grignard's, we already know that you could take and add a C- to the carbonyl carbon. So if you take this pair of electrons and move it down here, and then take that pair of electrons and bring it over to the carbonyl, and then move a pair of electrons up like that, basically what I'm doing is I'm taking the entire ring and adding it as if it was like a Grignard, because it's adding as a C-. And so you end up with a double bond here, the C double bond O with the O- over here, and then your double bonds here and here. There is an H here. So this is sort of like the mechanism of adding an electrophile to the ring. You're not. But what we've done is we've destroyed the aromaticity of the ring. And so that ring wants to become aromatic again. And so what it will do is, and I guess there's a couple of ways to look at this. The way I don't know that I've ever looked at it this way, but what I would look at this as is a tautomerization, is how I would look at this. Because what I would do is I would bring this pair of electrons here, and then I would take, well, let's see, no, I wouldn't. I'm going to go the other way. I would take this pair of electrons and move it here, and then move that pair of electrons to grab the hydrogen. So I would look at this as sort of a ketone to enol tautomerism, although it's not really an enol. But I would look at it that way to say that we end up then with the OH group on top. We end up now reforming the benzene ring, and we've now added our carboxylic acid group to the ring, and then the final step would just be to add H+ to then protonate the carboxylic acid group, so that we end up, in essence, adding a C double bond O OH group to the ring. So that mechanism combines steps that we've done in the past, and so that's one where we could do the mechanism. The organometallic reagents, those mechanisms are at least most of them are out of our range. So this is where I would ask for the mechanism. And the context of this is that number one, this is an activated ring, and so it's reactive enough to do this reaction. If it was a deactivated ring, it's questionable whether this could happen. But since it's activated, it can. It's more reactive. And the whole purpose of this is I've now basically made salicylic acid. And if I take that salicylic acid and I now add to it something like acetic acid, then I'll react this OH group with the carboxylic acid, so that what I can do is I can then take the OH group and convert it to an ester. And so that's acetosalicylic acid. And that's aspirin. Right. So the historical significance of aspirin, it's probably still the most taken drug in the world, I would imagine, because it does, all sorts of things, from cure headaches to be a blood thinner to is that it came that the whole sort of history of aspirin was that it salicylic acid you get from birch tree bark, and so the people knew if they chewed birch tree bark that it would cure their headache or whatever, because the salicylic acid that was in it. But the problem with salicylic acid is that it's a little bit the phenol portion. The OH attached to the ring is the phenol. The phenol has, it kind of tears your stomach up over time. And so they found that if you converted that phenol to an ester, that it was much safer on your stomach than just the phenol itself is. And so then that led to the whole idea of the synthesis of aspirin, which was done by Felix Hoffmann. This was all done in Germany. So Felix Hoffmann of the Bayer company did this. I believe the Bayer company was spelled like this. It still is. The Bayer company became Mobay, which became something else. It's a German company. It's been around for a long time. But then the Bayer, the way I tell the story is, you lost the B and it became Bayer, and so that was the Bayer aspirin. So it all came from the birch tree bark and the idea of the synthesis. But there wasn't enough birch tree bark to isolate enough salicylic acid to make aspirin, and so they had to come up with sort of an industrial way of making it. So they had plenty of phenol, because aromatic compounds like this come from coal, and Germany had tons of coal. So they were able to take all the components of the coal, all the aromatic components, and separate them so there was enough phenol. And so they found an industrial way of making the salicylic acid and then converting it to the ester. So that's kind of the whole context of that synthesis. But what it does is it reinforces what we already have talked about. So that would be a mechanism. And then nucleophilic aromatic substitution, both of those mechanisms are something that I usually ask about as well. So I think those are the three mechanisms. That and the nucleophilic aromatic substitutions are what I would, those are the mechanisms that I might ask. What else?
But just to clarify, is the Friedelcraft constellation used to then do Clemmensen reduction?
Yes.
So is there no Friedelcraft reaction to add anything onto the
No, there is. There is. The Friedelcraft's acylation is used to add a carbonyl group to the ring and make a phenylketone. So, for instance, I could take any acid chloride, and with aluminum trichloride, I can add that carbonyl group or that make the ketone out of it. And one of the purposes of Friedelcraft's acylation is if I then wanted to reduce this down by either Clemmensen or use the Wolff-Kishner reduction, I could then reduce that down to the straight-chained alkyl group. But I can also put carbonyl groups on the ring just to put carbonyl groups on the ring. So that's not its only purpose, is to make a straight-chained hydrocarbon. That's just one of its purposes. And you need to do that sometimes to do the different syntheses. In other words, depending on the molecule that I give you and say, give me a series of reactions to put these two groups on the ring, you sometimes need to put the carbonyl group on the ring and then reduce it. And that's kind of the one that we ended class on yesterday, where I said, how do you go from here to here? And how do you make this meta-substituted when both of the groups that we ended up with were orthopara substituents? How would you do that? That would involve this doing a Friedelcraft's acylation. Maybe we should do that one. I just have to remember what it was. What was the one I ended up yesterday? I took a benzene ring. I said how we want to work our way to taking a benzene ring and putting what two groups on it. A bromine was on top. Wasn't there a more complicated one? Is that what we ended with? And the one at the 3 position was NO2 and H2. Okay. Well, let's do as a problem this one with the bromine and the nitro group. and then we'll tackle the ethyl and NH2 group with them being meta, despite the fact that neither of those two groups are meta directors. But if I give you a problem, which I probably will, if I gave you a problem and said, go from benzene, let me put this in so I have a pointer here. So let's say I say go from benzene to this molecule using steps, using any number of steps that you need. There's always more than one way to do this. It doesn't matter how many steps you take, as long as you get there and you don't do any reactions that don't exist. There are no difficulty points. This isn't like diving, so that if you take 10 steps, you get more points than if you take 3 steps. So the more steps you take, the more likely you are to make a mistake, but that's not, as long as you get there, you're fine. And so what we need to do if we're going to do these kinds of problems, and this is ultimately what synthetic organic people do. They take A and they make whatever letter of the alphabet out of it you want to make. Usually like a D or an E would be great, but sometimes it's M and N and maybe S. So you got to go through all those different steps in order to make your product. So the first thing you have to do is you have to tell me, what would I need to add the bromine and what would I need to add the NO2 group? And so you should probably, think of those reagents. So how would I add a BR? So I'm going to need to do BR2 and FeBr3. Now you could say, after talking about the diazonium salts yesterday, you could say, well, I want a more complicated synthesis, so I'll make the diazonium salt and then I'll add copper bromide to it, which would also add the bromine. But that's going to be like 5 steps instead of 1. But if you want to do that, that's perfectly fine. How would we add the NO2? By adding, so HNO3, H2SO4, and so we have 2 reactions here that we can use to add the 2 groups. Next thing is order. So what should I add first? So in other words, I'm going to have to convert the benzene to the substituted benzene and then take it to the final product, because I've got 2 reactions and I've got 2 steps here. So what should I add first? Add the NO2 first? Is that what I should do? Agree or disagree? You have one person agreeing with you. Well, it assumes you're right. Don't be high-fiving yet. Any more people agree? So why do you agree? You want to add the bromine first? Okay, how many people want to add the bromine first? Okay, so you want to add the nitro group because the nitro group is going to direct meta. Okay. And what is this final product? It's meta. So we have to take into account the substituents. The pattern here that I'm using. So if I added bromine first, I would put the bromine on, but then where is the bromine going to direct the nitro group? Since bromine is a deactivating group, but it directs ortho and para, it would direct the nitro group to the ortho and para positions. Remember, the group that you're adding does not self-direct. It does not self-direct. So the group that goes on the ring is going to do the direction. So in this case, I would have no choice but to add HNO3, H2SO4 to put the nitro group on the ring, and then add the Br2, FeBr3 in order to add the bromine, because this nitro group is now going to direct to the ortho position. So we have to consider here the group, what group goes on the ring, because it's going to do the direction. Which is why tomorrow at the beginning of class I'm going to give you the chart from number 1 to number 10. You're going to have to fill in the groups. I'll fill in hydrogen. So you'll have to fill in the 9 remaining groups, and then you'll have to tell me whether they're activating, activating or deactivating, and then you'll have to tell me whether they're ortho-para directors or meta directors. It is a meta director. So what it's going to do is it's going to direct to the meta position, which is 1, 3. So it's going to direct meta to itself, and that's going to put the bromine up here, because the bromine and the nitro group in the original molecule are meta. And what you'll see when I do these problems, which means in the answer key, what you'll see is that I'll put the nitro. You might say, why'd you put the nitro group here? I put the nitro group there because that's where I had it in the final product. So I'm trying to put the groups so that I can line them up at the end. That's why I put them in the positions that they're at. So if we started with bromine, we would get ortho and para products. So we have to be careful of our substituents in terms of putting the group on that's going to direct to give us the correct substitution pattern in the final product. So in this case, it's got to go nitro first, then bromine second. So then the issue becomes, what about that molecule? What about the ethyl and the NH2? And so if I want to make the ethyl and the NH2, so I want to take my benzene and I want to make the ethyl group go there, which I'm going to put the real structure in. And I want to put the NH2 group there. My first step is going to be, what reagents can I use to put the ethyl group on, and what reagents can I use to put the NH2 group on? All right, so I'll give you a minute or 2 or 3. Write the reagents. You just have to write the reagents down, like one at a time, and write those on your board to add the ethyl group, and then the reagents I would use to add the NO2 group. So what reagents would I use to do that? And then if you wanted to be really creative, you could try and work in some of the organometallic reagents from today, but you don't have to do that right now. Maybe I'll give a couple problems here where it would be helpful to do that. So what do I need to add to make ethyl, and what do I need to add or use to make the NH2? Okay, that's the first one. So now about the second one. Okay, so now take it. Yes, okay. Yep, you're good. You're good. Yep. So now how do you put the NH2 group on the ring? So you got the you guys got the ethyl. Now put the NH2 on the ring. Oh yeah, you can use as many steps as you need. We're gonna work past just a single step here. I might use for the second step the zinc and the zinc iron HCl that we talked about yesterday. I mean, I would give you credit for that, I think, but the more traditional way would be zinc. Okay. Okay, I like your reagents. I'm not sure that your order is going to give you meta. If you do one thing and change your order, you'll get meta. But you got the right reagents. Okay? You got one extra carbon in your second one, right? Because you got a propyl group instead of an ethyl group. That's okay, and the first one is okay too. So if you're getting your if you've got the two reagents down to add the two groups, what I'd like you to do next is I'd like you to try and use the order of those reagents to make the meta product. So if you've got both reactions, now think about, okay, how am I going to structure those two reagents to make the the meta product, not make the ortho or para products. Okay, so you've got both of them, so now how do you put them together to make that product? So that's okay. So this is okay, and that's okay. And now if you want, take those reagents and put them in order to make just the meta. So that on. Now, okay. So now try and put those together so that you make. Okay, so then So if we did it, so this. Okay, so now what you want to do is now you want to order those so that it's just meta. You want to order the reagents so it's just meta. If we list this one, then it's like so now you want to order those reagents so you can get just the
Wait, I'm confused because why is it red?
So yeah, and so what you have to do is put this group on first, then put that group on, and then because once you have that on there, it'll be NH2. Once you have the NH2 on there, it'll go sort of like parent. So then your ethyl group will go with the parents and that. So you got to put it out here while you have. So that's what the H2 So if you so if you put the nitro group on and you reduce it, and then you put that on there, and that's going to direct work on parent, right? So maybe while this group is on there, you would want to have the alpha group, and then you turn yes. So if you do this is a little bit parallel. So maybe when you're here, add that group. And then change the other two. So you can do that.
I don't know why.
Yeah, so yeah. Wait, yeah. That's all. So I could move on. Yeah. I mean, and the thing is, you can do it that way.
Yeah, that's not.
You can do it that way. It's just you want to make sure that the reactions give you the meta product. So you can make the group first, you can do it. And you have a different way. So you want to put this on, you can go there. Yeah. And actually, you put the alpha group, you can put the curve on, you can do it on first, and then it would correct the nitro one. Then you can reduce on because it's a meta product as well. Okay. And then, yeah. Okay, so let's see. So it looks like we're, you know, you have to take each step. So if you want to put the ethyl group on, you need CH3, CH2, Cl with an AlCl3. That's one way to do it. You could put the ketone on and then reduce it with like a Wolff-Kishner or Clemenson, and that would be perfectly fine. Your automatic reagents to put an NH2 group on the ring are going to be putting the NO2 group on the ring and then reducing it with tin or iron and HCl to make the NH2 group on. So you put the NO2 group on with nitric and sulfuric. So we just have to get the reagents right. So the best way, well, there's no best way to do it, but one way to do this would be to say, okay, let me put my nitro group on first. I would like to put my nitro group on first because that's going to be a meta director. So now, if I take my nitro group and I say, now let's react this with ethyl chloride and aluminum trichloride, I'm now going to then add the ethyl group, and the nitro group is going to direct the ethyl group into the proper position. Because if I change the nitro group over to an NH2, it's orthopara. If I put the ethyl group on first, it's going to direct orthopara. So what I need is I need somewhere along the line to have a meta director, and in this case, this way the nitro group is going to direct the ethyl group, and then finally if I reduce that with iron or tin and HCl, I'm going to then reduce the nitro down to the amine. So half the battle is knowing how to put the groups on the ring. The other half of the battle is getting them in the right order so that the groups go in the right positions. Now you could have done this slightly differently. You could have said, and I'll just throw this out here because we may need to use this in the future. I could say, well, you know, I'm going to use the acid chloride and do Friedelcrafts acylation, and I'm going to put the carbonyl group on. The carbonyl group is now what kind of director? Sorry if you didn't hear me. The carbonyl group is what kind of director? It's a meta director. So now I could say, let's add my nitro group, and the nitro group would then be directed because of the carbonyl group to the meta position, and then I have to just reduce those two groups down. So I would say, well, I'll just use Wolff-Kishner to reduce the ketone down to an ethyl group, and then I would reduce the iron, tin, HCl would then be used to reduce the nitro group to the NH2 group. And so I could make the molecule that way. It's probably one extra step, but again, it's not about the steps, it's about getting there correctly. So you could use this approach. So there's usually more than one way to do these problems. If I gave you one or two, and usually what I'll do is I'll give you a couple could include three, and then if I give you three, then I'll usually say do two of them, you know, or choose two to do. So I usually give you a choice of which ones to do. But that's the way you want to approach it to make sure to get your reagents that way. And so yesterday we talked about all the different groups to be able to add the reactions you need to use to add all those groups onto the ring. I would strongly encourage you to either make a 3x5 card stack of those reagents, or you could even put it on a piece of paper so that you have all those reactions sort of at your fingertips until they get into here, so that way you can look and say, okay, well, this is the series of reagents I'm going to need in order to get this group on the ring. And then you can think about the order Because if the groups at the end, if the groups you put on the ring are not directing to the positions you want, that means you have to somehow put a group on and use it as the director to add the other group and then change them over. So let's see, what would another, and well, before I give you another problem, what were the point of all these organometallic reagents? Like the Gillman reagent is, it's very easy to make an organolithium compound out of benzene. All you do is take a bromobenzene and react it with lithium metal, and you will make your organolithium. An organolithium reagent is exactly like, in this class, it's exactly like a Grignard. So it's like having the benzene ring with a minus and an MgBr plus on the other side. But, and we didn't talk about this when we talked about Grignards, but you could have said, you know, I've got a carbanion here. I've got a strong nucleophile. What's stopping me from reacting this organolithium compound with something like ethyl bromide and doing an SN2 reaction? Right? I technically have a strong nucleophile. Okay, it's a strong base. But now we've been through alkoxides and now the alkynyl anions that we've done SN2 reactions to make like Williamson ether synthesis, and we've used it to make the alkynyl anion to alkylate those. So what's stopping me from doing that with a Grignard reagent or an organolithium reagent? And what's stopping me is they don't do this. They just don't do it for whatever reason. So they don't do SN2 reactions. Now if they did, that would be a carbon-carbon bond formation, and that would be, we'd use that all the time, but it doesn't work. So what we have to do is we have to modify then the Grignard in order to make it do this SN2 reaction, although it's not an SN2 anymore. And so what we do is, what somebody found out, and it was Gillman, and what he found out was that if you took and you reacted the organolithium with copper chloride, what you would end up doing is you would end up forming a species that where you would have two of the anions and then a lithium plus and a Cu plus, all in the same molecule that's reacting. And I'm not up on my Gillman chemistry, not even up on my organolithium chemistry anymore. But this changes the species that's reacting. And copper is, number one, copper's annoying. Because copper does like 10 different things. And it usually never does what you want it to do. You can mix copper with different reagents and they'll be green. The products will be green and purple, and they're vary in color, they vary in structure. I think I still have a couple of them in my lab when I had a colleague who was into copper chemistry, because there are proteins that use copper and they're bright blue, and they're called blue copper proteins, and so it's not quite sure how they react. And so somehow she she got me involved in this, and it's like everything that was made was a different color. We made bright green ones, bright green crystals of copper, and got a structure of them. And then the student came and brought purple ones to me, and she's like, they're not green anymore, they're purple. And I'm like, well, how does that happen? And then she goes back and looks at her notebook, which is the key critical part of keeping a notebook. And she goes, oh wait, I forgot to add this, and so now it's purple. So then I'm like, well, let's send it off to get a crystal, send off the crystal to get a structure of it. They could give me a partial structure of it. No one's ever gotten it because it does something weird that only one lab in the world can apparently handle. Which I didn't send it to that lab and say, can you do this? But when you add copper to stuff, it just changes the reactivity. And so Gillman found that out. He had no idea. He didn't care as long as it worked. That's synthetic chemistry. As long as the reaction works, you're fine. We'll leave it for the mechanistic chemists to figure out how it works. And then 10 years later, they found out how it worked, and Europe already moved on to your newest reaction. So there's mechanistic chemistry, which is called physical organic chemistry, which combines the two best chemistry subjects of physical chemistry and organic. And none of you are either going to take or have taken physical chemistry, but it has, it has about the same reputation as organic. Which isn't good, right? Every doctor I meet's hated organic and tells me up front, which is why I never tell them initially that that's what I do. I teach chemistry. Oh, general chemistry? Yeah, sometimes. Mostly organic. Oh, I hated that. One told me that sucked for me. She's like, that sucked for me. And then proceeded to tell me her story of organic, which apparently was from somebody who looked like Gabriel Byrne. Not David Byrne of the Talking Heads, but Gabriel Byrne of, of The Unusual Suspects, which has the other person we're not allowed to talk about anymore, in it. Which is that's the only reason why I'm in class, because he looked like that. I have no idea. It's a date, and I have no idea. I didn't meet anybody who looked like him when I was there a few months ago. But they tell me it sucks. And it's it doesn't suck for me. It may suck for students, but it doesn't work for me. Anyway, so if you're trying to figure out the mechanisms of these, what Gillman found was that when you take and you convert the organolithium to the cuprate, and this is called a lithium cuprate, you can then add any alkyl halide you want to this, and it will then couple. And so the coupling term means that it's a free radical mechanism, not an SN2 mechanism, so that you can now couple the benzene ring with the R group to now make any alkyl benzene you want by using this lithium cuprate. The issues with this reaction are that this, like a Grignard, the organolithium, like a Grignard, is air and water sensitive. And so you're limited in the solvents that you can use. We're now at a point in organic synthesis where we have two choices to be super environmentally friendly. Number one, we don't use any solvent. Or number two, we use water. Those are our top two choices if we want to be environmentally friendly. This is neither. So while it works great, it's kind of fallen out of favor. Fallen out of favor to what? To Heck, Suzuki, to those couplings that now allow you to use water and do the reactions. Yes, they require transition metals, some of them palladium, or there's probably a ton of these similar reactions that use ruthenium. Palladium's not cheap, but if you do the reaction and you filter the catalyst back out again, you can use it again. So the Heck coupling, the Suzuki coupling, they've all won Nobel Prizes for these reactions. The reason for those is because now I can do this in water. And if you really were going to go on and study synthetic organic chemistry, what you would find is that most of the reactions that we talk about are not done in synthetic chemistry. There's a tremendous number of organometallic reagents that everybody uses. And so synthetic chemistry at the higher levels doesn't even look like organic chemistry. It looks more like organometallic chemistry. And so this is our one time to sort of for us to introduce this, for me to introduce this kind of to you. And so that's why we include this. Plus occasionally the ACS exam writers like to throw in a couple of problems on this. So then you're like not looking at it going, what was that? You're looking at it going, did we do this or not? And the answer will be yes, we did do it. So the Gillman is just an easier way to say, look, I can couple an alkyl group with a benzene ring. And I can couple any alkyl group I want with the benzene ring. You might say, why? Well, why is that important? I want to make that molecule. Which I'm going to have some difficulties with, but I'm going to ignore those. And then maybe you can point out the difficulty I would have. But let's say I wanted to make this. How do I put that group on there? SO3H, SO3H2O, or H2SO4, I can put that group on one step. It's how do I put this, how do I put that group on there? Which is basically adding a 1, 2, 3, 4, 5, a pentyl group at the 3 position. So how do I do that? If I don't know about Gillman, or if I don't know about Suzuki, or if I don't know about Heck coupling, how do I put that group on the ring? Well, can I add the whole thing at once? How am I going to add a carbon group to a ring? Well, okay. Here's how we might want to do it. I might want to put a bromine on there and make an organolithium. And then I might want to add that organolithium compound. What can I add to that to make that? Carboxylic acid with this would make well, actually, carboxylic acid with the organolithium here would just deprotonate it. All right. Maybe this is throwing you. So we'll change it over to a magnesium. So what kind of reaction am I going to do? Give me a name. What kind of reagent is a magnesium bromide? Grignard. So I need to do a Grignard reagent, or Grignard reaction. If I want to do a Grignard reaction on this, what kind of functional group do I need to add to the Grignard? Carbonyl. So I need to add a carbonyl. That carbonyl could be what? An aldehyde, ketone, acid chloride, ester, carbon dioxide, right? Those are the kinds of carbonyl groups that we added to the Grignard. Now you might say, I need a little bit of color here in terms of being able to highlight these molecules. So what part came from the Grignard? The red part. What part is going to have to come from the carbonyl? What? Yeah, the rest of it. Exactly. So this part, all this part has to come from the Grignard, or from the carbonyl. So when a Grignard reacts to the carbonyl, what does it make? An OH group. I'm making a tertiary alcohol. So what kind of carbonyl did I need to add to that Grignard? Ketone. So now I look at this molecule and I say, you know what? I need the ketone of that. Here, let me put it sort of, kind of in the same orientation. How about that? That's the ketone I need to add. So over here, that's the ketone that I would need to add so that the Grignard comes in. Then H plus. So that I can make that molecule. So actually that one wasn't that bad, because I could add that entire group. Oh wait, nope, sorry. Never mind, we're not done yet. Because all we've done is we've added now that piece, but I still have that OH that I need to get rid of. But at least I put the skeleton of that alkyl group on there. So how am I going to get rid of the OH? All right, you want to convert it to a tosyl chloride or to a tosylate ester? I'm fine with that. I'm not fine with the iridescent purple. So let's change that OH over to a tosyl chloride. Could have used, or an alternative would be to use SOCl2 or PCl3. In other words, convert the oxygen to a potential like leaving group. So I could do that as well. So what could I do to get rid of the chloride or get rid of the tosylate ester? And by get rid of, what do I mean? Convert that group to an H. Convert it to an H. The tosylate ester is going to be far easier to do this with, by the way. So I want to replace this tosylate ester with an H. So what should I react it with? Okay, let me ask the question a little bit differently. I would like to substitute that tosylate ester with an H. What kind of reaction might I want to think about? I would like to substitute that group with an H. What kind of reaction should I think about doing? That didn't work. What kind of reaction do we want to do? Substitution. I could probably go on full teacher voice here, for the entire class period. You may already think I am, but trust me, I could make it even more stereotypical. So if I want to do a substitution reaction, wait, what am I trying to substitute? The tosylate for an hydrogen. So how about I add H minus? Where'd the H minus come from? Could come from NaH, could come from sodium borohydride. And that would take me to the final product. So we could get there. We have to remember all these reactions, which then, during a longer semester class, I would then say, oh, well, that puts all those reactions now into play for the next exam. So if you forgot about them, you can't. But what's my point? That's a good question. What is my point? And I know what my point is. This is just for drama. My point is that when we start wanting to put complicated alkyl groups on a benzene ring, if I don't know anything about these coupling reactions, how many steps do I have to do that? Normally I got to do a Grignard reaction, which gives me an alcohol, then I got to somehow get rid of the alcohol and turn it into an alkane. There's at least one more way that I could have done this process and turned that alcohol into an alkane. I could have very easily said this. I could have said, okay, I have my OH group. Let me go ahead and convert that OH group into a double bond. So let me put a double bond here and there, right? And then I could have said, well, then let me get rid of the double bond to now make the group that I wanted. Anybody have any ideas what I would add to either one of those? Yeah, and I probably want to protonate the OH, and I'll probably, to make the double bond, I'll want to apply some heat. So how do I convert an alcohol to an alkene? H2SO4 and heat. And then how do I convert the double bond to the alkene to an alkane? Forget about the Na and the H. Or sorry, the Na and the... You said Na and H2? Get rid of the Na and the N. Just H2. Will the H2 touch the benzene ring? Nope, super stable. So you could do this as well. But if you know about the Grignard, the Gillman, you know about Heck, you know about Suzuki couplings, then you can add that group all at once. So you, for instance, could very easily say for Gillman, you could say, okay, I've got a bromine on here, I'm going to add lithium, and I'm going to convert that to my organolithium compound. I'm going to add copper iodide to that to now convert it to the Gillman reagent, the lithium cuprate, and then all I have to say is, there we go. I can take whatever group I wanted to add on, put a bromine where I want to make the connection, and it goes on in that step. Now, in this synthesis, when I put the SO3H group, I'm going to have to do all this step, and then I'm going to have to add my H2SO4 SO3 to that to then put the SO3H group, because that is a sulfonic acid, and so if it's on the ring when I try and make the Grignard or try and make the organolithium, that sulfuric acid is going to kill the Grignard. So I'd wait until the end to put the sulfonic acid group on. And in our discussion yesterday about when to invoke sterics and when not to invoke sterics, large alkyl group I'm putting on. This alkyl group directs ortho and para. Ortho is going to be pretty sterically hindered, not only because the group next to it's sterically hindered, but the group I'm trying to put on is sterically hindered. So I would say, I could very easily argue on paper, 100% para, because the sterics are aligning to make that SO3H group always have para. So that's really the use of these coupling reactions, of these Ollie, Suzuki. And when they say coupling, it means it's none of these are like SN1s, none of them are SN2s. They're all transition metal, which means there are probably some free radical type stuff involved, mechanism. But that's the context in which these are put in. I can now add complicated groups. And see, and I'm not even asking you, hey, how would you make that? Right? I'm just letting you, oh, I'll just use that. I'm not asking you where's it come from. If I'm doing it, the first thing it comes from like Sigma Aldrich, the company that sells it. But if that's a big drug molecule that you can't buy, then what you got is you've got one group working on the benzene ring part, and usually it's not a benzene ring, usually it's a much more complicated structure. And then you've got another group working on this part, so that when they finish their part and the other group finishes its part, then you do Suzuki or Heck or something like that, bring it together and couple those two complicated parts together. Or you might have three parts and you've got three different groups or three different people, or you've got three different syntheses to make these different parts, and then you hook them together. That's modern drug design. And then if each one takes like 5 steps, which you'd be lucky if it took 5 steps, then people are going from A to B, and then they're losing a lot of product. So then other people are bringing up more B. Then when you go from B to C, you need more B, and so people are bringing up more B, and so you're constantly working product through the cycle to get you to that end point. And then there are purists out there when you do the synthesis that say, well, that's a lovely synthesis. That's creative. And sometimes you do get creativity points for putting these things together. Like when you go to publish it, it's like, well, you just made it. Well, that was the point. Well, you didn't use any creativity in making it. Well, I made it. And now we're at the point where you'd want to make it environmentally friendly as possible. Don't put any chromium in it. Don't put any mercury in it. Don't let it see chromium. Don't let it see mercury. And of course, let's make it for the cheapest price we can. Which does not include the $60,000 to $90,000 chemists working on it. 60 probably entry level, probably 6 figures at the PhD level. But then that would lead to a whole discussion about drugs and cost, and we will never go there in my class. These are things that people forget about. Or the number of drugs that are successful that make it to actual development as opposed to not making it there. That is in no way a justification sometimes for the cost of the drugs, but there's a lot that goes into making a successful drug. Including chemists. So that's the multi-step synthesis part. So what I would suggest is that for these like organometallic reactions, that we should think about making a sort of a chart of, okay, here's the 2 pieces, here's the 2 parts for Suzuki, here's the 2 parts for Heck, here's the 2 parts for Gillman. And there are some practice problems in today's folder dealing just with these. But they're all coupling. They're all putting 2 alkyl groups together. the most relevant part is making one of those benzenes so that now I can do my syntheses. So, what are your questions about? All right, let's take our 5-minute break, and when we come back, I should probably ask you to do a nucleophilic aromatic substitution mechanism, since nobody asked about either of those mechanisms. All right, so the other part of today's, besides the couplings, is nucleophilic aromatic substitution. Okay. Did that mechanism did those two mechanisms make sense? You have to know the mechanism, so I'll say I could ask you one or both of these on Monday's test. Let me re-ask the question. Did these mechanisms make sense now that you know that? They're the two for nucleophilic aromatic substitution. No. They did or didn't? Did they? Okay, that's what I'm asking. Now, why that's dependent on whether or not it's going to be on the exam, it's like my freshmen when I ask them, well, if you have a quiz at the end of the week, how are you going to study for it? What kind of quiz is it? What does that make any difference?
Well, I don't know what assessment it is. That's how you study. Would you not adapt your study skills?
And then Monday you got to
So if it's multiple choice, what are you going to do? You're just going to guess? This is what my freshmen told me. They said, well, if it's multiple choice, I probably won't study because I'll just guess.
Well, that's stupid.
Well, I mean, they were in their second week.
Well, for now, you might as well fill in all the summits and you have better chances to a higher percentage rate than if you lost on every single one. Statistically.
Are you going to study for the final? I mean, that's one of the
Well, I mean, they were in their second
Let's not
week.
talk about that. That was true.
Okay.
Not the one that it's right now.
See, that's why you have to put the same answer for anything. I guarantee you that is.
But I didn't think that. I was wrong.
Okay, so it's not just the students here that have a unique approach. I don't know how strategic it is.
How would you study for the
I would study for any quiz or test. I would, in theory, so that I knew it well enough that I could teach it to somebody else. But that's what we call.
For the level of knowledge, it's to the format.
But that's metacognition. That's a deeper level of learning that.
Sometimes
You don't have time for a deeper level of
Like,
learning. You got a
different
lot
formats
of
throw you off. Like, honestly, the final was like,
Oh, that was jarring.
it was like jarring.
It was jarring.
Like, we were so used to just running around mechanisms. And jarring.
I was confused when she kept saying like such bad stuff about the lab final. And she would say, she told us like only 2 people in the past 5 years have gotten A's, and she was like,
Why?
be careful, everyone's.
I think the
And then.
for which one, lecture or lab?
Yeah, and we were so scared. She was like, whatever you have is probably going to be lower after the final.
No, in general, it's good.
Well, that's true too. So those were truthful statements. I don't know this. I'm now going to invoke the wall between lecture and lab, which I normally don't do, but I'm going to separate lecture and lab and not talk about lab. Okay. Nucleophilic aromatic substitution. Nucleophilic, not electrophilic. So I'm going to react nucleophile with the benzene ring. So what am I going to make in this mechanism? I'm going to substitute the chlorine with an NH2 is what I'm going to do. I'm going to substitute this chlorine with an NH2 minus. Now with, bless you, the ring can either be activated or unactivated. Now since we only talked about activated yesterday, this is the opposite activation that we talked about yesterday. Because yesterday we did electrophilic aromatic substitution.
Are the rules just like opposite?
Sort of. The rules are sort of the opposite. So in other words, if I want to activate this ring, I need to add what yesterday was a deactivating group. So the activating groups in nucleophilic substitution are usually NO2s. And they are strategically placed at the ortho and para position to the group I'm trying to get rid of or substitute for.
Is unactivated in the same area as deactivated?
It can be that I put a methyl group on. Yesterday methyl was activating. This in nucleophilic it's going to be or deactivating. These two mechanisms are separate. So these two mechanisms are kind of the opposite of each other, and at least they are in feature. So typically an unactivated ring for again, this is nucleophilic aromatic substitution. So for nucleophilic aromatic substitution, the way I think about it is if it's got NO2 groups, it's activated. If it doesn't, it's not activated. The only reason I put that methyl group there in the unactivated was because when we really do this reaction, we end up with the NH2 group, both meta and para to the CH3 group. If the ring is activated and I was to add something like NH2 minus to it, if it's activated, I would clearly just replace the chlorine at its position with an NH2 group. So it just substitutes at its position. But when it's unactivated, you get both the both the meta and the para products. So when people did this reaction, from the first reaction, if they just used the chlorine without another group attached, they would have just said, oh, the NH2 replaces the chlorine. But when they put another substituent on the ring, they found that, wait, I get two different products, so my mechanism has to match up with getting two different products. So I'm going to ultimately substitute the leaving group, which is going to be like a chlorine. I'm going to ultimately substitute that with either an NH2 minus. I could do this with an OH minus. Oftentimes when you're using an NH2 minus, this might be done in liquid ammonia. So again, we're using a really harsh reagent. With either of these two unactivated reactions, it's going to usually require a high temperature in order to get this reaction to go, whereas if it's activated, it's going to require a lower temperature. So these two have different mechanisms. And so that's what I was outlining in the video and the notes was it depends on whether it's activated or deactivated or unactivated as to what the mechanism is. Let's do the unactivated first. So whatever mechanism we write here, it has to be consistent with getting equal mixture of meta and para substituted products. And so the way I would approach this is, or the way we do approach this is we say, okay, we're doing unactivated first. So we'll use NH2 minus as our nucleophile, and the chlorine's going to be the leaving group. So the first step in this mechanism is for the NH2 minus, or under high temperature the OH minus, to come in and deprotonate the hydrogen that is ortho to the chlorine. And so you can kind of think of this as an E2. So the NH2 minus is going to grab that hydrogen. The pair of electrons is going to go to form a triple bond, and the chlorine is going to leave. So I will put in quotes here E2 because it looks like an E2 mechanism, but it's not. And so this leads us to the famous benzyne intermediate. The benzyne intermediate has issues. The biggest issue is what should be the geometry of a triple bond? It should be linear. So putting a triple bond into a six-membered ring is difficult. So this is a really unstable intermediate. But it's kind of the only intermediate that explains how we get para and meta. So once you form this high energy benzyne, a second equivalent of NH2 minus comes in, and it can now add to, I'll label these carbons A and B, it can now add to A, or it could add to B, and there's nothing stopping it from adding to either one, so it's going to add 50-50. So when NH2 minus comes in and adds to carbon A, the pair of electrons in the triple bond is now going to move to carbon B. So I'm going to form the NH2 carbon bond. I'm going to then go back to a double bond, but I'm now going to have a minus charge ortho to the NH2 group. And if this reaction was done with NH2 minus in like liquid ammonia, then that minus would come and would then deprotonate the ammonia to give me the final product where the nitrogen has been substituted for the chlorine at the para position, and then the hydrogen would go back on. So this would be the formation of the para substituted product. If, on the other hand, the NH2 minus comes in and adds to carbon B, and again, there's nothing preferential here. Then what'll happen is that you'll end up now adding the NH2 minus meta to the CH3, and now the negative charge will go on the para position, and again with an NH2 or with ammonia, that minus charge will come in, grab that hydrogen, and I will now end up with the NH2 group being meta to the methyl group. And so you're going to get a mixture of meta and para substituted products. So without having that methyl group or another group present, you wouldn't know that you would go through the benzyne intermediate. Now perhaps somebody said, I wonder if this goes through a benzyne intermediate, and then somebody else may have said, or they may have said, well, that means if I put a group on there, I should see both, I should see 50-50 meta and para, and when they did the reaction, that's what they found. So it's either they found that, had to adjust the mechanism for it, or they had a mechanism and they further tested the mechanism by saying we should get these two products. If you're proposing a mechanism, it's always good to bust your own mechanism before somebody else does. Usually publicly or privately when you turn in or when you submit your paper and a referee goes, yeah, I don't think so. Usually they'll say, I don't think so, but if they say, I don't think so, and here's some evidence for it, then that's part of science. So the benzyne then is it is a very high energy species, but that's how the mechanism is written for an unactivated system. So that one's relatively straightforward. Deprotonate, make the benzyne, add the nucleophile to both cases, and then the final negative charge just deprotonates ammonia. So that's unactivated. And that mechanism is fairly straightforward once you see it. All right, does that make sense to everybody? I probably went through it that way in the video as well. Now, what about the activated one? So the reason this is activated is because I've changed the rules. Yesterday, when I'm reacting a benzene ring with an electrophile, I want the benzene ring to be as rich as possible, electron rich. So the donating groups pushed electrons in. That made it go faster. The withdrawing groups made it go slower. Since I've changed the rules and I'm now doing this with a nucleophile, any groups that withdraw electron density are going to activate the ring. And the way the nitro groups activate the ring, and they have to do this at the 2 or the 4 positions, is because the first step in this mechanism, and I'll just use NH2 minus to make the two mechanisms the same. In this case, what's going to happen is the NH2 minus is going to come in and attack the carbon, and then the double bond pair of electrons is going to go to the carbon with the nitro group attached to it. So I'm going to end up having the chlorine and the NH2 group attached to the same carbon, but now the negative charge is going to be on the carbon with the nitro group. So now what we need to do is we need to write out the structure of a nitro group. So remember, a nitro group has two resonance structures that have an N double bond to O and an N single bond O minus. That's a nitro group. And the reason that those withdraw electron density from a benzene ring is because you've got an N with a plus charge, but you also can draw a resonance structure, removing electron density, and put two O minuses in place along with a double bond to the nitrogen. So this nitro group then is going to stabilize that negative charge that I just made by being able to draw this resonance structure. So if I take this pair of electrons and I move it here, that pair of electrons moves there. And so I've still got my Cl, I've still got my NH2, but now I have a double bond to the nitrogen with now two O minuses. So that resonance structure now, the ability to draw that resonance structure stabilizes that. So the nitro groups, if they're going to be able to draw these resonance structures, they've got to be positioned at the ortho position, because that's where the negative charge is going to be formed. Is there another resonance structure I can draw? Yeah, there's two more. So I could take this pair of electrons, I could now move them here, and move that pair of electrons to the carbon that has the other nitro group attached to it. So now it's going to put a double bond there, and the negative charge now next on the carbon next to the other nitro group. So now I've got a third resonance structure. The only reason I can draw I could draw this resonance structure regardless, but the negative charge is always going to want to be next to a group that is withdrawing the electron density, and the nitro group is the best. And then you could take this pair of electrons, move it here to form a double bond, and move that pair of electrons off the nitrogen. So now I can form my last resonance structure. There's actually two double bonds. Missed that one. Did I miss any others? Oh, and the nitrogen is always positive charged. So there's 4 resonance structures that stabilize this carbanion intermediate, having the negative charge next to the nitro group, and then having the negative charge being taken up by the nitrogen, or by being taken up by the nitro group. So the reason this is activated is because when you put electron withdrawing groups at the ortho and para positions, then you can stabilize the negative charge. And if you can stabilize the negative charge, then you activate the ring. So if I was to ask you to do this mechanism, I would ask you to write the resonance structures of those intermediates. I would ask you to write these 4 resonance structures. So then, to end this, we go back to the first one. We go back to the first resonance structure, which is this one. And I'm going to change colors here. And so what's going to happen is this negative charge then is going to go back to form the double bond, and now either the chlorine or the NH2 group is going to leave. Which one's the better leaving group? Cl all day long. What makes a good leaving group? There's only one thing. A good leaving group is a weak or poor base. So which one's a weaker base? Cl minus or NH2 minus? It's no question. Cl minus. So then the Cl minus is a better leaving group, and so it leaves. And so what I end up with? I end up with the final product, which now has the NH2 substituted for the Cl. You could do this same reaction with a hydroxide. It's got to be a fairly stronger nucleophile to overcome that last step. So it's got to be a poorer nucleophile, stronger base than a chloride. And so this is the mechanism for activated. It's technically only 2 steps, but there's 4 resonance structures you have to draw. And I'm trying to remember. I think these intermediates are called the Meisenheimer intermediates. I don't think that's the benzyne intermediate. I think these ones are called the Meisenheimer intermediates. And that's with an M, not Meisenheimer, not Weisenheimer. Weisenheimer is sometimes used if somebody's a wise or a smart, and then something that follows that. So these are the Meisenheimer intermediates. Whoever that person is, they don't get enough publicity. So if you want to do nucleophilic substitution, and by far and away nucleophilic substitution is not as stressed as electrophilic aromatic substitution, but if you wanted to do it, then you're best to activate the ring by putting nitro groups on it. So those would be the 2 mechanisms for nucleophilic substitution. And I think if you look at older exams, you'll see that I've asked one or both at various times. And does that make sense to everybody? So just sort of a practical issue. Remember we talked about this yesterday? Or trinitrotoluene. And there is an issue of a lot of trinitrotoluene in sediment, in soils, hopefully not in water samples where the creek runs through the sediment or somehow it leaches down into the groundwater. You know, if you have an aquifer and you're on a well. If you look at what the structure of trinitrotoluene is, and then the question is, how did it get in the soil? Well, I mean, it got there near arms munitions places because it was, you know, if you made dynamite, it might have gotten out into the soil surrounding the plant, or if you were dropping bombs to test them out, it certainly might be there as well. And we don't drop a lot of bombs nowadays, but we did back in the day, before like World War I or World War II. So if you have this in your soil, one of the ways you might say, well, how do I sort of either convert this into something that's not, you know, as toxic, or change it? You might think about, it's got the nitro groups in the perfect position to be activated. The only issue is, whatever it is, I've got to get rid of the CH3. I've got to make the CH3 a leaving group. But if I could somehow figure out how to do that, then I could have that methyl group leave, and I can convert the TNT into maybe something that's a little less toxic. I know somebody gave a seminar a few years ago where they're kind of like, well, if you take this and you do nucleophilic substitution on it, you might be able to remove that methyl group. And I think an argument ensued about what the mechanism was, and it was this Meisenheimer intermediate. So that's nucleophilic substitution. So that's different than electrophilic substitution. Could you do nucleophilic? Could you incorporate a nucleophilic substitution into your synthesis? I don't know, probably could. If you did, number one, you're not necessarily under the restriction, so you could say, you'd have to say nucleophilic substitution, but if you wanted to say, oh, I have a chlorine and I'd love to make a phenol out of it. Or I'd like to add an OH group to the ring, which would probably be a better question. If you wanted to add an OH group to the ring and you're stuck and I don't know how to do this, then you could say, well, I'll just put a chlorine or bromine on it, and then I'll react it with hydroxide under high temp nucleophilic aromatic substitution and replace the chlorine with the OH. And depending on the mood that I'm in when I grade your exam, I might go, oh, that might work. Full credit. Because what you proposed could occur. But otherwise, how would we have to add the OH group to the ring? How do we add an OH group to the ring? In the final step, yes, H3O. But what's that H3O reacting with? What kind of molecule? The diazonium salt. Where did the diazonium salt come from? NH2 plus. Okay, so diazonium salt came from NH2 plus NaNO2 HCl. Where'd the NH2 come from? Fe or Sn and HCl reacting with a NO2. And then how did we get from benzene to NO2? Now, did I just give you permission to forget about that and just say, well, we'll do nucleophilic aromatic substitution on an alkyl chloride? No. Because that could be one question all to itself. I could say, show the series of reactions to go from benzene to phenol and put an OH group on the ring. All right, so I mean, it's 3 steps to diazonium salt. NO2, NH2, diazonium. So I would spend a little bit of time getting those steps down. The other alternative is what I have up there, is you could put a chlorine on there and you could invoke the nucleophilic aromatic substitution. If you invoke the top one in a synthesis, like I said, I probably would accept it. But I'm still going to get this bottom one in on the exam one way or another. So you got to know, you have to know how to get to the diazonium salt, because the diazonium salt lets you add the OH or the C triple bond N. So if I give you a synthesis with a C triple bond N in the final product, you got to go through the diazonium salt. Or if I gave you one with a fluorine, you'd have to go through the diazonium salt. This is the diazonium salt, the N triple. It is the gatekeeper to OHs and C triple bond Ns and Fs and Is. So it will let you put an F, an I, a C triple bond N, and an OH on the ring. It also will let you put a Cl or a Br, but you know another way to do that. So we talked about that yesterday, and we sort of wrote the different reactions. These, so the Cn was copper cyanide, Ki, the F, I believe I wrote something like NaBF3 or something like that. And then the OH was H3O+. And then, once you put an OH on the ring in this lecture for today, it's important to remember that once you put the OH group on the ring and you would like to convert that to an OCH2CH3, what would you do? Or if you wanted to convert the OH group to any kind of ester, what would you do? Here's the problem. Here's the problem before you go any further. The problem is the OH is attached to the benzene ring. So if you want to say make it a tosylate ester and then substitute for it, that doesn't work when the OH group is attached to the benzene ring. What am I trying to make? And nope. C double bond. That's C double bond O. I'm trying to make an ether. How do I make ethers? I might, again, if I'm in a good mood, I might accept adding ethanol and acid to this phenol. And if I was not in a very good mood at all, and you gave me that, I might say, well, show me the mechanism by which that would happen, if you want credit. And protonating the OH on the ring and having it leave will never happen. So you'd have to say, well, I'm going to protonate the OH on the ethanol, and then I'm going to do an SN2 reaction to kick the water off. So is that legit? Yeah, it is, but not for the mechanism that you may want to show me. I don't know, I was thinking ether synthesis. Williamson ether synthesis, that sounds familiar. So if I wanted to do Williamson ether synthesis, what should I do? I should convert the OH to an O minus. And then I react the O minus with okay. First step, how do I make the O minus? H minus, NH2 minus, what else? Na, or K, there's two more. A C minus, then there's one more that we may or may not have talked about. This is a phenol. Phenols are more acidic than normal alcohols, so you could use hydroxide for this. a hydroxide will completely deprotonate a phenol. So that would be, so this step would be, that would be using Williamson. I don't know. That's a good question. First, you have to know your reactions. Because if you don't know your reactions, it's like spelling not knowing what letters are. Or it's like writing sentences and not knowing what words are. Or it's like writing sentences with knowing the words but not knowing grammar. So, no, that's the whole thing. Making the alkoxide, or in this case the phenoxide, and then reacting it in an SN2 reaction is Williamson. But there's the reason that was in these notes is because we have to remember that we can make ethers this way. And it even says phenoxide, Williamson, it's the exact same molecule. How do we make the ester? Here's our alcohol. What am I going to add to that? I'll forgive the people that aren't in lab. We're going to take this and we're going to add that. So we're going to take an alcohol and what are we going to react with it? I gave you a bottle of an alcohol and a carboxylic acid. And so you react that with H+. And that is called Fischer esterification. Why am I stressing this? Why am I going back over it? Because just putting an OH group on the ring is great, but putting an OH group on the ring and then being able to convert it to something else is like what you're gonna have, what you may have to do. Particularly with the Williamson ether synthesis, because when did we last do that? We did it on Monday, hopefully. Correctly. Okay. All right, so tomorrow we will start with the quiz. Fill in the chart. Tell me if it's ortho para or if it's meta and activating or deactivating. And then we will pick up and we may go back and do a couple of synthesis problems, but we'll also do aldehydes and ketones. Okay, so I have your exam.